In podcast 18, the second of the physics podcasts, we're going to take a more detailed look into friction. So friction occurs when things rub against each other, and it's a force that opposes motion. So what that means is that if something is already moving, it's going to tend to slow that object down, or if an object isn't moving and there's a force that is attempting to move it, then friction will try to prevent that from happening, try to prevent it from moving. So let's take a look at this example here. There's a car driving along and the engine is pushing the car along, and this red arrow here represents the force from the engine. Now we can see the airflow over the car, and that airflow is a kind of friction, and that friction is attempting to slow the car down. So I'm going to draw that as a blue arrow pointing in the other direction. So this arrow represents the air resistance, we could say, or the friction, and the red arrow represents the push force from the car. Now if the push force from the engine became smaller, we can see that friction is now bigger than the push force, and it's going to tend to slow the car down. If I put my foot on the gas pedal again and make the push force from the engine bigger, it's going to tend to speed the car up. So note that the friction force here is in the opposite direction to the movement of the car through the air. Let's take a look at a second example. So in this example we have a slope, and we have a book sitting on the slope, and the book's not moving. Now if the book had wheels, gravity, or a part of gravity, the component of gravity pointing down the slope, would cause the book to roll down, but the book is not moving. So what force is preventing the book from moving? And that's friction. Friction in the opposite direction. So I've drawn these arrows the same length as one another because the part of gravity that's pointing down the slope is exactly balanced by the friction force pointing in the other direction. So the book stays where it is. So in the first example, the car is being or attempted to be slowed down by the friction, and in the second example the book is not being allowed to move because of the friction. But friction can help us move in actual fact. Let's take an example of walking, an everyday action. So when we walk, what we do with our feet is we push back on the ground. Now this red arrow represents us pushing on the ground. Just going to make that a little longer. When we push on the ground, our feet don't slide across the ground because of friction. And what the ground does is it exerts a friction force back on our foot. So the friction force allows us to propel ourselves forwards. So the red arrow is us pushing back on the ground, and the blue arrow is the ground pushing back on us. Without the friction, our feet would simply slide around. Now let's take a look at that book again and put it on a flat surface this time. Now if we take a force sensor and we push the book so that it slides at a steady rate, we're going to be recording push force. But this force is actually also equal to the friction force in the opposite direction, because if we push at a steady rate and the book slides at a constant speed, then we know that the push force and the friction force will be balanced. Now what determines the size of that friction force between the desktop and the book? Maybe the following. Maybe the contact area, maybe the speed at which you push the book, maybe the type of surface or type of surfaces, both the desktop and the book, or even the weight of the book. Now it so turns out that we find only the last two affect the friction force that we measure. So in addition to that, or developing from that, we find that the friction force is proportional to the weight. Now when we have a proportionality, we have a proportionality constant, and in this case that proportionality constant here is called the coefficient of friction. The symbol is mu, a Greek letter mu. So mu or the coefficient of friction, depends on the nature of the surfaces. So again, this is the equation. F is friction force, mu is the coefficient of friction, and N here is, well, it's sort of the weight of the object, but we're using the symbol N because more specifically it's the force pushing the two things together, or the normal reaction force, which is why I've used a different symbol. But if the surface that we have our object on and that we're sliding the object on is flat and level, we can just take N to be the weight of that object. So if we rearrange that equation, we can see what the coefficient of friction actually is. So rearranging the equation, I'm dividing through by N, and I get mu, coefficient of friction, is F over N. So it's actually the ratio of the friction force to the object's weight. Now at this point I'm going to do a virtual experiment using a friction applet to demonstrate coefficient of friction. So in this applet I have the ability to change the weight of the object, and in this case it's books, and I have the ability to measure the friction force by pulling with a Newton meter. So here's the applet. Here I have one book and I've got the Newton meter there, and I can drag the Newton meter and record the force, 2.45 newtons to drag one book. It's telling me the mass of one book is 1 kilogram, and as we know, 1 kilogram, multiply that by 10, its weight is approximately 10 newtons. So here I've prepared a data table. Mass 1 kilogram, weight 10 newtons, 1 times 10 is 10, and the friction force 2.45 newtons as recorded from that experiment. Let's go back, add a book, and drag again. 4.9 newtons. Now if you look carefully, you can see that I need to drag with a force greater than 4.9 newtons to get it moving. But when it's moving at a steady rate, 4.9 newtons is what I record. So let's go back and add that to our data table. 2 kilograms, 20 newtons, 4.9. Add another book, and again drag, 7.36. Again notice that the force goes above 7.36 before it starts moving. 3, 30, 7.36. Add another book, 9.81. Let's put that in. 4 books, 40, 9.81. And finally, add a final book, 5 books, that's 5 kilos. Click and drag, 12.26 newtons. Again, notice how it went above that before it started sliding, and then it went to a stable value. 5 books, 50 newtons, 12.26. Just a brief comment on why the value was higher than the stable value once it was moving. We have two kinds of friction, static friction and dynamic friction. Static friction, we see that before the object starts to slide, and it's bigger than the dynamic friction, which is what we get when the object starts to slide. So static friction is larger than dynamic friction. So back to the data table, there we are, and here's my graph. It's just really a rough sketch graph, but I've plotted friction against weight. Now we know from the equation that the coefficient of friction is friction divided by weight. If I divide the y-axis by the x-axis here, that's what I'll get. So the slope of this graph is the coefficient of friction. The slope of the graph is the coefficient of friction. So Excel will quite happily work out the slope of this graph for me, or I can calculate the rise over the run to find out what the coefficient of friction is. So that's what I've done here. Slope is coefficient of friction, 12.26 minus 0 divided by 50 minus 0 gives me 0.25. So the coefficient of friction for these surfaces, the book and the surface that it's on is 0.25. So here's a table of some examples of coefficients of friction. Graphite, like pencil lead on steel, has a very low coefficient of friction, 0.1. Concrete on rubber, for example, rubber-soled shoe walking on the sidewalk, much higher, around 1. We need that because we don't want to slip over. This is why we use rubber-soled shoes, as opposed to graphite-soled shoes maybe. Wet concrete, spelt wrong, on rubber, if it's been raining, we know that it can get slippy. So the coefficient of friction drops significantly if the concrete is wet. Finally, steel and PTFE. PTFE is a coating which is often used to make surfaces very, very slippy indeed, and we can see that the coefficient of friction is really small, 0.04. So, in summary, friction is a force that opposes or attempts to prevent motion. On a flat surface, it's the ratio of measured friction force between an object and the surface and the object's weight. But more generally, it's the ratio of the friction force between the two surfaces and the force pushing them together, which we can call normal reaction force. And here's the equation. Mu, the coefficient of friction, is equal to friction force divided by the normal reaction force, or the weight. Static friction, which is recorded before movement actually happens, is larger than the dynamic friction, which is what we observe as the object is actually moving.